Alright, let's take a look at this math problem. A woman went into a bank to cash an insurance refund check. By mistake, the teller gave her dollars for cents and cents for dollars. She put the money in her purse, but accidentally dropped a nickel on the floor. When she got home, she found that she had exactly twice the amount of the check she had cashed. She didn't have any money in her wallet before going to the bank. What was the exact amount of that check? Now, at first glance, this looks like a word problem that may have an algebraic solution. Perhaps a system of two equations and two variables. We're going to try an algebraic approach to solving this problem. The first thing we need to recognize is that there are two totals in this problem. One is the total amount of the check that she went to cash. The other is the total amount of money that she had when she came home. Or perhaps the total amount of money that the banker gave her after she cashed the check. We're going to try to construct some equations to represent the information in this problem. Our first equation will deal with the total amount of the original check, and we're going to use the letter K to represent that amount. K is the amount of the original check that she took to the bank. Now, the amount can be expressed in terms of dollars and cents, and of course a dollar is worth 100 times more than a cent. So we're going to use cents in our problem, and we will express everything in terms of cents. So for the number of dollars, it'll be 100 times the number of dollars. That'll mean for each dollar we'll have 100 cents, and then of course the amount of the cents. That's the amount of the original check in terms of dollars and cents. Now, the second total was the amount that she had when she got home. And the amount that the banker gave her was based on the check, but he switched dollars for cents, and we can easily represent that by switching the variables C and D. So we'll have 100 cents for each cent, and we'll just have 1 cent for each dollar. Now, of course, on her way out of the bank, she dropped a nickel, so we're going to have to subtract 5 cents from this problem to take that into account. Now, at this point, we have two equations, but unfortunately, we have three variables. And there's not going to be an algebraic solution to a system of two equations and three variables. You're going to need to have at least three equations. You need at least as many equations as there are variables. But nevertheless, we're going to go ahead and see what we can do to simplify these two equations before moving on. One thing we could do, pretty simply, is eliminate the variable k. We can alter the first equation so that it says 2k. Actually, this should have said 2k, not k2. And what we're going to do is simply multiply everything in the first equation by 2. So the k will become 2k, the 100d will become 200d, and the c will become 2c. Now we have two equations that both say 2k equals. And because 2k is equal to the right-hand side in both senses, we could actually rearrange these two equations, combine them into one like this. 2k and 2k are the same thing. Something like this. But of course the first equation tells us that 2k is actually equal to 200d plus 2c. So we can replace that right here. And the second equation tells us that 2k is equal to 100c plus d minus 5. So we'll put that right here instead of 2k. Now we have just one equation, and we've eliminated the variable k. But here again, we don't have enough information to reach an algebraic solution. There are two variables in this equation, but there's only one equation, and we would need at least two equations to solve for two variables. But we're going to continue and simplify this equation. We'll go ahead and get all of our variables on the left side and all of our constants on the right side. And what we'll do is we will subtract d from both sides to get rid of that d right there. And we're going to go ahead and subtract 100c from both sides. Something like this. And in so doing, we'll end up with a new equation That looks like this. 199D minus 98C equals -5. It's probably about as simple as we can get this problem. We've got all of the essential information from the word problem, and we still have two variables. The best hope we could have would be maybe there's another equation we can construct based on the information in this problem. But having gone through the problem, there is really not enough information for another equation. But there is some implicit information in this problem. And that information has to do with what numbers are valid for C and D. When we talk about the number of cents that could be written on a check or given to somebody as pennies, we realize that these cents have to be whole numbers. In fact, they have to be whole numbers between 0 and 99, because you can't have less than 0 cents handed to you by the bank teller, and you wouldn't have more than 99, because then that would just be part of another dollar. So C has some constraints, and maybe we can make a note of that. C has to be between 0 and 99. C is greater than or equal to 0 and less than or equal to 99. Now for D represents the number of dollars, and I suppose 0 could be the smallest number of dollars, and there's probably no upper limit. Now these are some basic constraints that we have on our C and D variables, and also C and D must both be integers, because we're not going to be dealing with a fractional number of cents or a fractional number of dollars. This is the only implicit information in this problem that we didn't include in our original equations. And after doing a little research, I discovered that this is a different class of problem. Let's take a look at Wikipedia. Here, where are we with the Safari? This is what we call a Diophantine equation. Diophantine equation. Now, this was a particular branch of mathematics, we'll donate later, and it deals with polynomial equations where there are more unknowns than there are equations, but critically, there are only integer solutions. And here's a classic example right here on the right. This is a right triangle with two sides, A and B, and a hypotenuse C. And they're all integers, A, B, and C. And of course, according to the Pythagorean theorem, if you sum the squares of A and B, you'll have the square of the hypotenuse, the diagonal length, if you will. So it says the word Diophantine refers to the Hellenistic mathematician of the 3rd century, Diophantus of Alexandria, who made a study of such equations and was one of the first mathematicians to introduce symbolism into algebra. The mathematical study of Diophantine problems that Diophantus initiated is now called Diophantine analysis. Now, there are a lot of different ways of approaching these kind of problems, but if you want to get an idea of how different these are than just regular algebra, just take a look at this paragraph. Diophantine problems have fewer equations than unknown variables and involve finding integers that work correctly for all equations. In more technical language, they define an algebraic curve, algebraic surface, or more general object, and ask about the lattice points on it. So we're dealing with something that's considerably more complex than just a regular system of equations. Now, here's another critical piece of information. While individual equations present a kind of puzzle and have been considered throughout history, the formulation of general theories of Diophantine equations was an achievement of the 20th century. So this is actually a branch of mathematics that's still an area of research, if you will, and definite approaches have been developed in more recent times. Now, there's a lot of information in this article, different types of equations and how to solve them. Interesting side note here is Fermat's last theorem is in the same family and wasn't solved for over 350 years after Fermat first mentioned it. And it was only solved in the mid-90s. But let's see here. Somewhere in this article is an example of a problem very similar. Yeah, here we go. Typical problem. The given information. A father's age is 1 less than twice that of his son, and that the digits A, B, making up the father's age, are reversed in the son's age. So for example, if the son was 37, the father would be 73. And it leads to the equation 10A plus B equals 2 times 10B plus A. That's because the father's age is twice that of the son, so they're multiplying by 2 here. And of course, we're multiplying the digit in the tens place by 10. And then the father's age is 1 less than twice of his son, so there's a minus 1 here. This can be simplified just like we did into this equation, 19b minus 8a equals 1. There's not a lot of direct approaches to solving these kind of problems. In fact, there are probably infinite number of solutions if we don't restrict the variables to integers. We could pop in some number for b, and we could just make up any number for b. And then obviously we could solve the equation for a. There would be some other answer for a. It doesn't really matter what we pick for b, there's going to be some other answer for a. It's only when we restrict the variables to integer values that we end up with perhaps a single solution or a small set of solutions. Now, one approach to solving these kind of problems is called inspection, and that basically just means simplifying your equations and just looking at them and trying to figure it out like a puzzle. If you look at this little equation right here, 19b minus 8a equals 1, if you think about that for a while, the answer may just pop into your head. If we multiplied a by 7, 7 times 8 would give us 56. And if we multiply b times 3, we would get 57. And of course 57 minus 1 is 56, or 57 minus 56 equals 1. So that is a solution, and it's just something that you discover by looking at the problem. Because we tend to think in terms of integers, our brains are able to do that. There's many other approaches that can be used. We're not going to take the time to go through this whole article. It's really a special branch of mathematics on its own. But one method that is discussed is basically trying a whole lot of inputs to see if any of them actually work. In computers, we would call that a brute force approach, trying every possible combination of numbers to derive a solution. And there's other methods as well, but since computers are really fast, and we can take that approach. So what we're going to do is we're going to write a little program incorporating the information in this problem, and then just have the computer try every possible combination. We'll cycle through all the values of c between 0 and 99, and we'll just keep incrementing d, starting with 0 and going up until somehow we find something that works. So let's write a little program here. And this website right here is a website where we can type in code and then run it, so you don't need to install anything on your computer. I'm using the language C++ because I'm familiar with it, and it's a strongly typed language, so we can definitely restrict things to integers and so forth. So let's take a look at this problem. First thing we're going to do is we're going to define some integers. We're going to define C and D. And we're going to loop through the value of the cents from 0 to 99. So this is what a for loop looks like in C. We're going to start by setting C equal to 0. And we're going to keep looping as long as C is less than 100. Okay, so the loop will stop when C gets to 100. So the largest number that will be included is 99. And what we want to do is at each step through the loop we want to increase C by 1. And that this plus plus operator here indicates to increase C by 1. Here's our loop, and the code inside of these brackets will be executed for each number, 0 through 99. What we need to do, though, is we need to also have a number of dollars starting at 0 and going up. So I'm going to create another loop on the outside here, where we start D off at 0, and we'll go ahead and maybe we'll go up to 1,000. It's probably safe. And go ahead and increment D. So this is going to be what we call an outer loop. I'll go ahead and indent the inner part of this. So the outer loop from here to here runs 1,000 times from 0 to 999. And inside that loop, we loop again 100 different values for C. So this is going to go for quite a while. And inside, we're going to put the key information that we're looking for. We're going to just calculate the totals. Total of our original check was equal to 100 times the number of dollars plus number of cents. And the total that she received from the bank is going to be 100 times the number of cents plus the number of dollars minus 5. Of course, the banker gave her cents for dollars and dollars for cents. So that is the calculation part of our inner loop. Now what we want to know is when the amount she got at home was exactly twice as much as the original check. So we're going to write an if statement to test that. We're going to say if K times 2 is equal to, and that double equal sign means is equal to rather than setting a value or storing a value. If the original amount she had times 2 is equal to the amount at home, okay, maybe saying that backwards would make more sense. If the amount she had at home, right here, was equal to twice the original amount, then we have found our solution. And we're going to output some information. We're going to say solution found, and we'll go ahead and output the value of dollars and cents. Number of dollars, maybe a period, number of cents, and then a blank line. And we'll stop searching at that point because we found our solution. This return 0 will cause the program to terminate. So let's go ahead and run this program and see what happens. Uh-oh. Something is wrong. Don't know what that's all about. I probably made a mistake in my program. Oh, this isn't algebra. If we want to multiply, let's go back and edit that. If we want to multiply a variable by 100, we actually have to put a multiplication sign in there. There we go. Sorry about that. Confusing. Save it. And let's run it. Waiting for compilation, running. Solution found, $31.63. So that's a brute force attack. We just try every possible combination of dollars and cents until we find one that works. Now if you want to, we could comment this line out. That means the computer will ignore it. And that means we'll keep searching for solutions after the first one and see if there's any more. Let's run it again. All right. There were no further solutions found. One thing you might want to try is looking for others. What if she dropped a dime instead of a nickel? No solutions found. What if she dropped a quarter? No solutions found. What if she dropped a 50-cent piece? Ah, look at that. different solution. Only one, at least up to $1,000. But her original check could have been $16.33. She could have dropped a 50-cent piece and then found out at home that her total was twice what her original check was. Anyway, hope you enjoyed the solution to this problem. This is just one approach to Diophantine equations.